To most executives, ISO 9001 suggests a sprawling bureaucratic checklist, a system designed primarily to generate endless compliance paperwork. Conventional corporate bureaucracy is agonizing. It functions as a slow-moving machine where identical documentation systematically bottlenecks agility and halts organizational innovation. The modern ISO 9001:2015 standard operates on a different logic. It is structured as a rigid, self-improving systems engineering architecture. Building this architecture required a structural change in the 2015 revision, the complete and deliberate elimination of the requirement for preventive action. Previous versions of the standard forced companies to document fixes only after systemic vulnerabilities had already caused operational friction. The 2015 replacement for that process is found in Clause 6.1. It is called risk-based thinking. Risk-based thinking fundamentally shifts the organization's stance. It moves the team away from reactive firefighting and into predictive architectural design. Replacing preventive action with risk-based thinking alters the organization's focus. The true intent is to move from merely surviving errors toward predicting and neutralizing them before they can manifest. This predictive capability is built into the high-level structure, known as Annex SL, which standardizes all modern ISO management systems into 10 mandatory, universally applicable clauses. Operational exclusions are no longer permitted by default. To bypass a specific clause, leadership must provide rigorous, written, systemic justification. These 10 clauses are driven by a central processing engine, the Plan, Do, Check, Act cycle, or PDCA. This diagram shows the continuous feedback loop required by the PDCA model. First, the strategic foundation is constructed. Clauses 4, 5, and 6 map directly into the Plan quadrant. Resource allocation and daily operations execute next, slotting clauses 7 and 8 into the Do quadrant. Data gathering secures clause 9 into Check. Finally, data forces operational optimization, filling the Act quadrant to complete the engine block. This architectural mapping ensures that all of your disparate departments operate smoothly within a unified, continuous feedback loop. Mapping the 10 clauses to the PDCA cycle takes a static compliance document and transforms it into a self-correcting organizational engine. Clause 6.1 requires risks to be quantified deterministically, removing intuition from operational planning. The frontline tool for translating business threats into quantitative data is the probability impact matrix. This grid plots the two core dimensions of any threat, the likelihood on the x-axis and the consequence on the y-axis. Plotting specific threats isolates the exact vulnerabilities capable of disrupting operations. Organizations can then use this specific data to precisely direct capital and resources toward the threats located in the high-impact zone. For a more granular calculation of these interventions, engineers use failure mode and effects analysis, or FMEA. An FMEA calculation relies on 3 variables: severity, occurrence, and detection. This formula converts those 3 variables into a singular actionable metric. Multiplying severity, occurrence, and detection outputs the risk priority number. This resulting risk priority number, or RPN, determines the organizational priority. This calculation provides an objective, mathematically derived priority rank for every identified vulnerability. Executives use specific RPN thresholds to decide whether they must avoid the risk, mitigate it, transfer it, or accept it. Replacing subjective judgment with objective RPN thresholds makes risk management an exact science. We can apply this FMEA logic directly to a real-world environment, a pathology laboratory. The lab identifies a critical threat in specimen labeling errors. The likelihood is low, but the impact on patient safety is catastrophic. This equation displays the initial calculation before systemic intervention. A probability of 2 and an impact of 5 results to an RPN of 10. By installing an automated barcode scanner to improve detectability, this single variable drops the final RPN to near 0. Patient safety is completely secured. Rather than asking staff to be more careful, the lab physically engineered the human error out of the system entirely. Now consider an automotive manufacturer relying on a single, highly specialized raw material supplier. If this single external supplier fails, internal manufacturing stops immediately. This supply chain diagram visualizes the initial risk calculation for a single point of failure, generating an RPN of 20. Qualifying a secondary supplier and restructuring logistics mitigated this threat. Splitting the flow drops the RPN to a manageable 10. Both the laboratory and the manufacturer used Clause 6.1 to move past identification. They implemented structural interventions to physically neutralize failure points. Implementing the system requires a specific chronological sequence, beginning with Phase 1, preparation. Phase 1 requires 1 to 3 months and centers on a gap analysis, comparing current operations to the ISO standard. Phase 2 is implementation. Over 3 to 6 months, a company rewrites its operational protocols to include the new risk controls. Phase 3 is the audit. This takes 1 to 3 months and requires internal stress testing followed by external verification. Looking at this roadmap, achieving full certification requires a disciplined commitment spanning 6 to 12 months. The financial cost of this deployment typically ranges from $5,000 to $25,000. Clause 10 requires this system to remain active. The goal is continuous operational optimization, ensuring the architecture improves as the organization grows. The ROI of this initial investment is a self-governing operational architecture. It creates a system that scales securely, predicts failure, and runs autonomously.